to succeeding. Okay. So we're going to pick up where we left off, and we're just going to jump right into it. So, of course, S is entropy, not to be confused with enthalpy, which we'll be talking about here in a minute again. S is entropy, and that's the measure of chaos or disorder. And delta, of course, is change in. So change in entropy of the universe is always increasing. A positive delta S means increasing disorder. Positive. So if it's greater than 0, it's positive. So the universe is tending towards more of a disorder. And actually, that's the second law of thermodynamics. But we need to remember that the universe actually is basically the system and the surroundings. So system plus surroundings equals the universe. Right? So we could have a change in entropy. We'll talk more about the system and the surroundings, I think, coming up. Okay. Oh, by the way, it said for spontaneous reactions. So we'll talk more about what spontaneity means coming up, too. I kind of said spontaneous means that it just will go from left to right as it's written. So.
Well,
what else would it do?
Yeah.
Well, sometimes it's favored. What we talked about, like product favored and reactant favored. So that would be a product favored sort of reaction. You can equilibrium. So we've looked at this before too, that you can, the change in entropy, in this case of the system, is what it started out, what it finally was, minus what it is at the end. What it is at the end, minus what it started out with, started as. Sorry. So it's always final minus initial. So it's the final entropy state minus the initial entropy state. And that big E-looking thing, of course, is sigma, means, yeah, summation, exactly. So we are going to apply this, this to chemical equations. Okay. It's a 3-year-old? It's pretty safe around here. So this is going to be feel vaguely familiar, and I'm just going to kind of show you working a problem here coming up. But anytime you see that little circle, that means standard conditions for thermodynamic problems. And standard conditions are 25 degrees Celsius, which is different than for gases. Standard conditions for thermodynamic processes are 25 degrees Celsius, 1 bar pressure, and if you have any aqueous solutions, the concentration of that solution is 1 molar. So that will be helpful. So that's what that little superscript not means. Standard conditions. So these are some entropies. Notice the not means that they are at 25 degrees Celsius. If they're aqueous solution, 1 molar and a pressure of 1 bar. And these are kind of things that we talked about and you did for your homework today. So for instance, if we look at carbon, okay, we see that in its diamond state, that has the lowest amount of entropy. It's the most ordered. In its vapor state, it's the most disordered. So, I mean, these things should make sense when you look at them. And you can find pairs, like we have water here, and it's gaseous state and its liquid state. Here we have C2H6 and C3H8. As you get larger, it should increase in entropy. So these are standard molar entropies, excuse me. Oh, see, now that's a typo down there. Look at that. Oh my gosh.
Oh, yeah.
Entropy. That's okay. Okay, so let's work a problem. We're burning CH4, we're burning methane. Of course, the products when you burn hydrocarbon are carbon dioxide and water. And this is balanced. So we're going to actually knock out, we're going to knock out 3 quantities. Yeah, I guess just 1 quantity. we're going to use the standard molar entropies, and we're going to knock out the change in entropy as the reaction proceeds from left to right. Okay. So it's going to be the summation of the products minus the summation of the reactants, basically. So here listed by reactants, 2 reactants and 2 products. So these are the standard molar entropies that we're going to use. So here we go. But it's always products minus reactants. Okay. So I like to kind of work it as 2 separate problems. Products, a summation of the products, I get a number. Summation of the reactants, I get a number, and I do 1 subtraction at the end. So looking at the products, yep, we have carbon dioxide and water. So the stoichiometric coefficient in front of the carbon dioxide was 1, so 1 mole of CO2. And then from the table, we had 213.7 joules per mole Kelvin. And then for the water, the coefficient was a 2, so we have 2 moles of H2O times 69.9 joules per mole Kelvin. And then if we go ahead and put that in our calculators, that will give us the product side, the summation of the product side. So we have 353.5 joules per Kelvin. And then we have to do the reactant side. So yeah, moles have canceled out, and we're left with units of joules per Kelvin. Then we do the reactant side, which was methane, CH4. The coefficient was 1, so it's 1 mole of CH4 times the constant from the table, 186.3 joules per mole Kelvin, plus 2 moles of O2 times the entropy, standard molar entropy, which is 205.1 joules per mole Kelvin. So the moles cancel, we're left with units of joules per Kelvin, and I get 596.5 joules per Kelvin. Now here's where we're ready to take products minus reactants. Okay, now remember this is our delta S term, so it looks like it's gonna be negative, isn't it? Delta S is 353.5 joules per Kelvin, which is the product side, minus 596.5 joules per Kelvin on the reactant side is equal to negative 243.0 joules per Kelvin. Which now, relate this to what we talked about on Monday, and the fact that you have a negative change in entropy, not enthalpy, negative change in entropy means, what do you think? Is it becoming more ordered or disordered?
More ordered.
Yes. Very good. You got it. That actually goes against Mother Nature. So this reaction is creating order as it goes from reactants to products. Perfect.
Is that common?
We're going to see here in a minute, the thing that balances out is what's happening with the same reaction with regard to enthalpy. So it's entropy and enthalpy that you can tell, does that make sense? Will it really happen in the forward direction? So, yeah, no, Mother Nature doesn't like that.
Yeah.
But it can be overridden. Okay, very good. So yeah, there's a whole bunch of tables, and I think I do like 2 of them. Now, you're going to see the G there. That's Gibbs free energy. Of course, enthalpy is H, and entropy is S. So these are like thermodynamic values. Molar enthalpy, standard molar enthalpy of formation, little f, Gibbs free energy of formation, little f, and standard state entropy. These all have little superscripts, I guess. So it looks like this. This is the first one of several. Now these are all inorganic substances. Sometimes you look at a table and you're like, well, what's the difference between this table and the next major table? These are all inorganics. Okay, and they're alphabetical. And here's where I say, I know. skip several slides, dot, 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 yeah. And then switch gears, this is the last of the inorganic. I know because it ends with the zinc. This is the last of the inorganic. And I think this is right. If you go back to the S column, the entropy, notice they're all positive. But the enthalpy of formation, the standard molar enthalpy of formation, there are some positives and negatives, aren't there? I think so. Okay. And then after that comes the organic compounds. So of course organic means it has carbon and hydrogen, maybe oxygen and some other miscellaneous nonmetals. Yeah, there's some positive standard molar enthalpies of formation, delta H naught sub Fs. But all the entropies are positive. Okay, and we're going to talk about that middle column. That's pretty important, Gibbs free energy of formation. So, organic compounds. All right. So, change in entropy, delta S, of the surroundings. So, remember you have system, surroundings, universe. Okay. So, I think we talked about this the other day, that, do you remember Q is equal to M C sub P delta T? Okay, so that's what that Q is. That's the change in thermal energy of the system. So the change in entropy of the surroundings, the change in entropy of the surroundings is equal to the change in thermal energy of the surroundings divided by T. So now here's the deal. I was looking at this in my office, and I'm like, oh, that's pretty cool. Okay, if you have, I'll make a little beaker down here. It's going to have to be small. Okay, if you have a beaker, and that's the system, it's purple is system, green is the surroundings. Okay, we know that, and I'll make black the universe. Okay, we know that energy can go this way, and energy can go this way from the system to the surroundings, from the surroundings to the system. And actually, that's the same thing with regard to entropy. The change in entropy can... So here we go. If it's an isolated system, wait a minute, I should say the surroundings are isolated from the universe, then the change in thermal energy of the surroundings equals negative change in thermal energy of the system.
How could the surroundings be isolated from the universe?
I know. I was like, wow, that's deep. If there's another universe.
Would that be like in a box or something?
Multiverse.
Like
Yeah, if the universe was the box. And we do assume that within the universe, energy is constant, matter is constant. Okay? So... yeah. Interesting. I know. Anyway, but you got the right idea. Yeah. You need to take astronomy. I'm just saying. I won't be teaching it, but you need to take it. Okay. So we'll take a look at these. And these I don't think you'll need your calculator for. They're just kind of a looking at sort of problems. Let's see, 17. Clear to chapters, or is it 19? 19, oh my gosh. Here we go. So I won't belabor these too much, but let's see what we got. So you have A, B, and C, and it kind of reminds me of what you did, I think, for homework already that you handed in, or you're going to hand in. Basically, indicate which one represents an increase in entropy. Now, if it's increase in entropy, delta S is positive, and disorder is increasing, just kind of like you told me a minute ago. Okay? Or is it a decrease in entropy, negative delta S? And in that case, order is increasing. Something get hot. Okay, so you should do okay with that. Let's see what the next one looks like. Oops, go back. Okay, this one is similar. Arrange them. This might, just take your time. They're all kind of related. So you have 3, and you're supposed to arrange them in order of increasing change in entropy. So increasing change in disorder, increasing disorder. And you kind of see what it starts at and what it ends at. Starts at and ends at. And my hint is make sure you consider both the phase change and the pressure. So for instance, A and B look very similar because they both have water going from a liquid phase to gas phase, okay? But in the case of C, it's going from a higher pressure to a lower pressure. And what do you think if it's going from 1 atmosphere to, wait a minute. Oh, hey, that's the other thing. You have to, I see now, that's the units problem. So we have units of atmospheres here and millimeters of mercury here. And do you remember 1 atmosphere is equal to 760? Very good. You got it. So you're going to want to convert millimeters of mercury to units of atmospheres probably. And you're going to see that's a big step down. So what happens if it decreases in pressure? What happens to its entropy?
It's less chaotic. No. So, no?
I think it'd be more chaotic. Let's see. Because it goes from being pressure of 1 atmosphere to being sparse. Or
Oh, the pressure is decreasing. Oh, okay. Yeah, so I was thinking like the size is decreasing, but if it's
it's almost
if
the
it was
size is increasing because it's...
Yeah, so if the pressure is releasing, it's,
Yeah,
okay, that makes sense.
I think so.
Okay.
And then this one is similar. I think it's all very similar. It's like, how do I do so many? Let's see. Oops, sorry. I think they're all very similar.
Okay.
Just kind of slightly different nuances to them. They're kind of fun, I think.